So it's kind of sad, but anyway. So today I'm going to be talking about the theories on how the solar system came to be. Okay, how the solar system was formed. So our solar system includes the sun, which is in the center, and all of the bodies that revolve around the sun. This includes planets, moons, asteroids, maybe an occasional comet that comes through. It also includes the asteroid belt, which is this giant field of asteroids from like the size of a pebble to the size of a moon that's between Mars and Jupiter. We'll look at that as we go through the planets, but everything's revolving around the sun, whether it's revolving around a planet that revolves around the sun. Ultimately, in our solar system, everything's going around the sun. Between the 16 and 1700s, scientists thought that the sun formed first, and then after it formed, it started throwing chunks of material off that became the planets. The planets are the 8, formerly 9, but the 8 major bodies that revolve around the sun, including Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, formerly Pluto. When I was a wee lass in school, there were 9 planets, but Pluto got demoted, I think in, I don't remember what year it was, 2005, maybe 2010. It's been a while that scientists or astronomers, astrophysicists, whoever it was, got together and decided that based on the definition of a planet, which is a body that dominates the orbit around the sun, they decided that Pluto doesn't, quote, dominate, because it turns out that the moon of Pluto is about 50% the size of the planet. So you can't really say it dominates over its moon, which is why it got demoted. Anyway, so what was the last point? Okay. Oh, right. Okay. Sorry, I was like lost my train of thought. So originally scientists thought that the sun was formed, and then the sun just kind of threw chunks of rock, I guess, out and then formed all the planets and moons. But in 1796, again, with everything, you do not have to remember names and dates. That's for history class. In 1796, this French guy named Marquis Pierre Simon de Laplace had a new idea of how the solar system formed. He said that the sun and the planets were actually formed at the same time, and they were formed from the same spinning nebula. Now, a nebula is, in that video when I showed you what we call the pillars of creation, a nebula is a cloud of gas and dust that's just out there in the universe, which is kind of a leftover of the Big Bang, right? It's kind of like, if you think of when something explodes, it's kind of like that dust that hangs in the air afterwards for, I don't know, about 13.5 billion years now. But you also have nebula that are formed when things explode. Like when old stars explode, they leave behind a nebula as well. So Simon de Laplace basically said the whole solar system evolved at the same time, not the sun first and then the planets. And this is called Nebular Theory, which shouldn't be too hard to remember because it's formed from a nebula. So here, we start first with a nebula. Scientists think that there used to be, where all of the sun and the planets are now, there used to be a giant, massive star, like several thousand times larger than our sun. And when stars are that big, it's kind of like, if you think about a big fire compared to a small fire, a big fire burns hotter and quicker. So large stars burn through their fuel quicker than small stars. So this star exploded in what's called a supernova, and it left behind this nebula, so this cloud of gas and dust. Now, the number one ruling law in the universe is gravity. And gravity depends on 2 things: size of objects and distance between them. So if at the center of this nebula, you have a more closely packed, dense area of particles, that's going to have more gravity than the areas around it. Now, we know that things that have gravity are going to start to pull material in towards them. As it pulls more material in, it gets more dense, which gives it more gravity, which means it can pull even more things in towards the middle. So it's kind of, what do you call it? Self-perpetuating. It keeps itself going. Now, eventually, when we look at how stars are made, the evolution of stars, and we look at our sun, you will find out that this kind of activity happens all the time in nebulae all over the universe. But there comes a point where, let's say, because inside the core of this nebula, you keep building up more and more material, and gravity keeps squishing it, right? Because gravity wants to pull things close together. So when you have a big, giant ball of hot gas like that, it has a lot of gravity, so it pulls in even more material, and that's going to increase the density at the core. And if you increase density, of course, that means that you are packing more particles in to the same area, the same volume. So if density increases, that means that pressure is going to increase as well, because you're putting more and more particles in the middle. And if pressure increases, temperature also increases. So it's kind of a chain reaction. So if you start off with even a smaller area where there's a denser area of material, it's going to have more gravity, pull in more material. Increased density increases pressure, which increases temperature. Now, at the point where our sun, or our star, which we call the sun, is born, there is a very magic number, which is 10 million degrees Celsius. At 10 million degrees Celsius, nuclear fusion begins. And I'll talk about that and the specific steps of that in a later chapter. But nuclear fusion, so nuclear, is the process that stars use to create energy literally almost out of nothing. Like, you don't need to put in energy to get the energy out. Once it starts, it keeps itself going for billions, that's with a B, billions of years, which is a miracle, kind of, like, not in the God sense, but in the holy crap, that's amazing science, in that kind of way. Because, well, I don't really gonna talk about it too much, otherwise I'm just going to keep going off on tangents. But this is the nebular theory, so we understand how a nebula kind of comes together to form objects. Now, while the sun took 99% of all of the matter from that original nebula, all of the planets and all of their moons and the asteroid belt, everything else in the solar system got the remaining 1%, just kind of like the scraggly pieces that kind of flew off further. If you think of like a bomb that goes off and you have most of the stuff that stays kind of hanging near where the explosion was, but you've got these big pieces that get like flown way, way away from the original explosion site. You can think of those as the planets, these big chunks that got flown far away. Okay.
Our solar system is the region of space which falls within the gravitational influence of our sun. The solar system is thought to have begun forming about 5 billion years ago from a giant spinning cloud of gas and dust.
That's the nebula.
The core of this cloud grew under the influence of gravity and became denser and hotter. As material fell towards the growing core, the cloud increased in speed and flattened into a giant spinning disk.
So one of the things that happens in the universe when you have material that's building up like this, it starts to what we call coalesce. Coalesce, I think that's how you spell it. There might not be an A, I can't remember. My spelling is not great, that's why we have spell check. But anyway, coalesce means it kind of comes together and it starts spinning. Just like if you ever watch ice skating and you watch the ice skater as his or her arms or their arms are out and they pull their arms in, they start to spin faster and faster. that's coalescing, and that's what happens at the center here.
Eventually, the increasing temperature generated enough energy to trigger nuclear fusion. This fusion marked the birth of our sun.
And that's 10 million degrees.
The lighter gas was swept far out into the solar system, leaving heavier, rockier material and metallics with high melting points nearer the sun.
So just to go back and review that again, when nuclear fusion starts, it is a huge, what do you call that? It's a very highly exothermic reaction. Obviously, it produces enough heat that we can like survive outside. So that original explosion blasted all of the very light elements like hydrogen and helium out of the solar system. All of the heavy stuff were left behind, like the solid Earth that we're on, and the cores of the other planets.
Leaving heavier, rockier material and metallics with high melting points nearer the sun. Molten metal and dust particles stuck together to form clusters, which in turn stuck together to form rocks.
So this is how the planets and moons are being formed.
Mutual gravity caused these rocks to come together, eventually to form planets. In the hot inner regions of the solar system, rocky planets with metal cores were formed. In the colder outer regions, things were different. Further from the sun, temperatures dropped. Water vapor condensed and turned to ice. This ice, combined with the vast amounts of gas blown away from the sun, meant there was a lot more material here than in the inner regions. As huge cores of ice and metal grew, the gases swept away at the sun's birth were attracted through gravity. When the accretion of most of the ice and gas was complete, we were left with the gas giants. The solar system as we know it is around 4.6 billion years old. It's looking pretty good for its age.
Okay, so from the Big Bang, we have matter that is gathered into clouds of dust and gas. That's the nebulae, can spell, nebulae or nebula if you're single, singular. And so the cloud of gas and dust that developed into our solar system, we call the solar nebula because solar comes from sol, which means sun. The solar nebula was much larger than what our solar system is now because it's all condensed. Now, they estimate that the formation of the solar system occurred about 4.6 billion years ago. So there was a supernova or some other force that caused the solar nebula to start contracting, and a star, which we call the sun, started to form in the center of that. When the temperature was high enough, 10 million degrees, fusion started. And 99% of the matter in that solar nebula became part of the sun. So then after that, you've got the formation of the planets. These formed in the outer regions. They started, if you saw in the video, like just those giant chunks of rocks that would kind of smash into bigger rocks and smash into bigger rocks. Those formed planetesimals. And then planetesimals come together to form what's called a protoplanet. And the gravity of these bigger and bigger chunks of rocks acted like a magnet because the gravity got so great, it started pulling in other planetesimals from the solar nebula. And that's when you saw from that video, when you had that kind of molten globe that was spinning really fast and kind of sucking everything in. That's this point, a protoplanet. Eventually, these protoplanets condensed into the existing planets and moons. A moon is a smaller body that orbits a planet. So a planet orbits a star and a moon orbits a planet. Both planets and moons are smaller and denser than the protoplanets were. So this is a photograph of Jupiter. And the reason why I added it is because this is, I believe this is Io, which is Jupiter's biggest moon. And I just think it's cool because you can see the shadow. That's the shadow of the moon on the surface of Jupiter. So if you have ever seen pictures of like Earth's moon versus Earth, and then here's Jupiter's moon, one of Jupiter's moon, it has like 160 moons, versus Jupiter, you can see when we talk about a planet dominates the area of its orbit, this is what we mean by dominate. It is obviously the largest object compared to its tiny, tiny little moon. Oh, okay, right. So this is Jupiter and what are called the Galilean moons. These are the 4 largest moons of Jupiter. I don't know what they are in order, but one of them is Io, one of them is Ganymede, one of them is Europa, and the other one is Callisto. Probably sounds familiar if you've studied mythology yet. I think a lot of these names were named, a lot of the planets and moons were named by the Greeks and Romans after their gods. Now, the distance between the protoplanets and the developing sun were going to influence what kind of planet it was going to become. You've got the 4 planets that formed closest to the sun are Mercury, Venus, Earth, and Mars, which you see here in order: Mercury, Venus, Earth, and Mars. You can see that Venus and Earth are nearly identical in size. These are called the inner planets. They are also called the rocky planets or terrestrial, meaning land, because they're made of solid rock on the surface. You could theoretically walk on each of these planets. In fact, I'm pretty sure we have two robots still on Mars now, if not more. Didn't the Chinese just land some, I think? Anyway, we're sending robots to Mars now that are just kind of like driving around and like taking samples. And I saw the other day, I don't think I bookmarked it, but there was a Martian sunset, I think, on Insta. Like basically a picture of the sunset, but from Mars. Pretty cool. But because they developed close to the sun I want you to think of as like a giant fan. Like think of the most powerful fan you've ever felt in your entire life. And that's the sun. But instead of blowing air, it's blowing like high energy radiation, like gamma rays and X-rays, basically things that will fry your DNA and cook you like bacon. So all of the lighter elements that might have been held by the gravity of these planets were blown away. And it's only until later on that Earth was actually able to form an atmosphere after the sun was like had calmed down a little bit after it started fusion. The next 4 planets developed far enough away from the sun. Again, you can see the shadow of one of the moons. Okay, if I don't want to cover it up, the shadow of one of the moons here on Jupiter. And right, so these guys were far enough away that they were able to keep a lot of their outer gases. Plus, it's like super cold out there. So a lot of things that are gases or liquids like water, methane, ammonia, things that are gas and liquids at our distance from Earth are frozen out there. So that's Jupiter, Saturn, Uranus, and Neptune. They formed in the colder areas. There was also a lot more like junk left over from the supernova beforehand. So it was kind of at the edge. It was able to pick up a lot more of that material. Again, like a water, methane, ammonia, the frozen gases. So to give you an idea of scale, this is a picture, obviously, of the sun, and then the inner planets to scale. So that's Mercury, Venus, Earth, and Mars compared to the size of the sun. It's just a little bit bigger than us. And I also just want you to keep in mind when you start studying the size of things, which is something that I'm going to try to emphasize and then just kind of remind you guys how insignificant human beings really are. So at the end of the day, don't take yourself or anything else in life too seriously, because we're like right there, right? We're a tiny, tiny little, like we're basically ants running around on a hill in the middle of like flying around this giant ball of fire. But I want you to picture this in your head and think about the longest flight you've ever been on. Like this, when I go home to visit my family, which I haven't been for many, many years, but when I did go home, it's almost literally halfway across the globe, like literally on the other side of the planet. And so there is no direct flight from here straight to Chicago. It's too far. So I had two choices. I could either, I don't think they do it anymore, but Thai Airways used to go to New York straight from here. That's 17 hours. And then from New York to Chicago, I think is another probably 3 or 4, maybe 3 hours. So let's just say 20 hours altogether. And just to make it really easy, let's just say it takes 24 hours to get halfway around our planet. Okay. And then look at the size of it next to the sun. And our sun is kind of a smallish star. All right. If you look at the sun compared to other stars, it's like, meh, not that big a deal. Now, these are called the inner planets. They couldn't build up gases because, one, they're small, so they don't have as large of gravity to hold gases to them, but also because the gases got blown away, by solar wind. Again, solar wind, think of it just like regular wind, but with like radiation that will melt your face. That's about as good as I can describe it. Because the outer planets developed further away from the sun and they're huge, so they have a lot more gravity, they were able to keep a lot of their original gases. So we also call them gas giants. Sometimes we also call them Jovian planets after Jupiter. So again, here's little old Earth next to Jupiter. And there's Earth next to Saturn. That's why we call them gas giants. Okay, now the formation of Earth, obviously it was quite hot when it was first formed. The Solar Nebula would have looked something like this. So you see the sun is kind of starting to form and you've just got all of these rocks and stuff that are like flying around, smashing into the protoplanet. 3 things contributed to the heat of the planet. 1, just from the collision of all the planetesimals, if you take like 2 rocks and like smash them together, sometimes you can actually get them to spark depending on what kind of minerals are in the rock. 2, the increasing weight of the outer layers as more and more material is smashing into it, it's getting bigger and it's squishing the inner layers. And when that's just from friction, it's going to create internal heat. And 3, there were just a lot of radioactive materials that naturally radiate heat, like uranium, plutonium, things like that, when Earth was first formed.
You may not recognize it, but this is our planet in its very earliest days. Little more than a few pieces of rock colliding as they circle the sun. These impacts were so violent they generated immense amounts of heat. And they also delivered vast quantities of radioactive material to the Earth. Eventually, when the outer layers of the planet cooled, these 2 powerful sources of heat were trapped in a huge hot core. The centre of our planet is as hot as the surface of the sun. This is the source of Earth's vast heat energy. And it's what fuels volcanoes to this day. trapped within our planet, Earth's hot core has been continuously releasing unimaginable amounts of heat. It gives you some idea how much when you realise that even after 4.5 billion years, there's still plenty left. Earth's inner heat makes the planet's surface incredibly dynamic. It has created a restless, continually changing landscape unlike any other in the solar system. It's a world of destruction and renewal.
So Earth is still extremely geologically active. Like he said in the video, it's pretty amazing when you think about the fact that we still have volcanic eruptions and earthquakes and all of those kinds of things, which comes from this molten core of the Earth, which is left over from 4.5 billion years ago, which is just kind of crazy, like that it's still hot, right? Still super hot. So the temperature on Earth when it was just forming was hot enough to melt iron. And so all of the really heavy elements were going to be pulled in towards the center, mainly iron and nickel. The denser materials are going to go towards the center, just like if you were to put something at the bottom, or like put something in a glass, it would sink to the bottom. Only in this case, the bottom is the core. The less dense layers are going to basically sort themselves out according to density. And so the lightest materials will make up the crust. Eventually, you've got 3 basic layers: crust, mantle, and core. It's actually a bit more complicated than that, but I'm not going to get into that because it's honestly not that important. Now, when Earth was formed, like I said, most of the gases got blown away because of the solar wind, and Earth is just not that big enough to hold a lot of the gases. But as collisions kept coming for Earth, the gravity increased, and eventually Earth was able to capture some of the hydrogen and helium that were in the solar nebula. So by the time Earth was actually kind of a solid form, the atmosphere was mostly hydrogen and helium. We still find these 2 gases today, but only in the upper atmosphere. Like I said, solar wind blew most of it away, but the second atmosphere that was formed resulted from explosions about 3 billion years ago. And this is when, again, we still have it occurring today with volcanoes, but imagine like, I don't know, like 10 million more volcanoes on the surface of the Earth. When volcanoes erupt, they put out a lot of water and carbon dioxide. And those 2 gases are going to form the second atmosphere. Sunlight probably caused ammonia and some of the water in the atmosphere to form nitrogen, hydrogen, and a little bit of oxygen. And because hydrogen is the lightest element, a lot of it escaped into outer space. But when we finally had early green plants start to form, that would increase the level of oxygen. Some of that oxygen is going to form ozone. Ozone is O3 in the upper atmosphere. So you see that between the stratosphere and the troposphere, you've got the ozone layer, and that protects all of life on Earth from radiation. And it actually allowed life to move from the ocean to the land. Now, before the oceans were formed, obviously super hot, and volcanoes explode, putting a lot of carbon dioxide and carbon dioxide and water into the air. Eventually, as the Earth started to cool down, all of that water vapor that was spewed into the atmosphere through volcanic eruptions started to condense and fell as rain to form the oceans and the rivers and all of that. Now, here's the key thing. To create a breathable atmosphere for animals, when the oceans formed, that amount of water was able to absorb a lot if not most of the carbon dioxide from the atmosphere. So by about a billion and a half years ago, the atmosphere that we see today was formed. So beginning of Earth, you don't have any atmosphere. After the Earth is formed, when it gets enough gravity, it pulls in hydrogen and helium. When it starts to cool down a little bit, you have a lot of geologic activity with volcanoes. Volcanoes are going to spew CO2 and H2O into the air. And then finally, when the Earth starts to cool down more, all of this, well, not all, but a lot of this water will fall as rain, forming the oceans. When the oceans form, then the oceans get to absorb the carbon dioxide, and you have what is today's atmosphere. Okay.